Sound good? Okay, so 17.4 is the standard normal curve, normal distribution. On page, go to page 660, they have several examples there of data, and that'll help us kind of analyze what the standard normal curve looks like. Not everything fits into the standard normal curve. What?
The black's not going
No,
away.
it's not going away. Yeah, it's committed. It is committed. And then there's the spray bottle without the cap. It's awesome.
No Ivan to clean the board.
No Ivan.
Aw.
He's on to bigger and better things. Okay, so the standard normal curve, not everything fits into that category. Man, this is the workout for the day. Oh. I wonder if somebody intentionally screwed up the ratio of permanent versus non-permanent in these markers just to like laugh. I mean, this thing, if you worked at Expo, the marker company, and you just slipped in some Sharpie ink, just thousands of people writing on boards.
2 sacks that tripped and put in a vat of Sharpie in another.
Okay. Anybody want a marker that doesn't really come off? Okay. All right. So standard normal curve, when we look at that information on page 660, we can see there the first one is last digit of telephone numbers. And they have 0, 1, 2, all the way up to 9. And they have that histogram, the bar graph, right? That type of data you can see wouldn't fit under the standard normal curve. Now, I say the standard normal curve or the normal distribution. What we're referring to is this curve that looks like this, where the bulk of your data would be in the middle. And so if you look at when you're looking at the histogram, if you will, of telephone numbers, I'm not drawing it completely to what they had, but it looks something like this, so on and so forth. This does not fit with the data, your data would be, let me do it, color, I don't, but your data would look like this, right? For a standard normal curve, you would have something like this, and your telephone, last digit of the telephone data, you can see, doesn't fit that. All this data is well above the curve, and so that doesn't work. That's not a normal, what we would call a normal distribution, where the bulk of your data is in the middle. It would be, and then you can look at the next one. It says the precipitation in centimeters from 0 to 1. There's 242 days in a Midwestern city. There's 99 days and 17 days. That data, you can see, also doesn't fit. It's here and then here, something like this. And if you drew a curve, that curve would look more like this, some sort of exponential curve coming down. It does not fit the standard normal curve, which would look like that. So that data wouldn't fit into the standard normal curve. If you were to look at, let's say, even in this class, when you look at standard normal curve, you could think of this and you can apply it to like this, and they have this for test scores for like SAT, ACT, and right. And so if you were to look at though like this class, the standard normal curve would say, hey, you're going to have kind of the bulk of people are getting C's, because the bulk of people are, if you will, average. It's like, okay, in a difficult class, let's say, right? In a class that is going to be challenging. So if everybody was taking the class, most people are going to get C's, and then you get down to the D's, and then you get down to the F's, and then you get to the B's, and then you get to the A's. Some breakdown like this where you say, yeah, most people are right in this range with C's. Then maybe you have a few people up in the A category, a few people flunking, and then that would be kind of a standard normal distribution of scores. If you look now with only like 5 of us in this class, right, is that if you looked at that, our data really is the bulk of it doesn't look like this. The bulk of the people would be, B up to A, something like this. Most of us have B's and A's. I think everybody does. So, you say, okay, that's actually the bulk of the data. That isn't fitting quite like a standard normal distribution because everybody's kind of like this. We're all kind of equal in our scores. What some teachers do is they say, well, that is not accurate because that means the class is too easy. Now, there's only 5 of us, and we've kind of weeded out, right, the chaff, if you will, is that, trying to fit this and make it difficult so only like one person gets an A, a couple of you get B's, somebody, or C's, and then somebody's flunking. That doesn't make much sense. But if you were teaching a class of like just a general class of 60 people, you might say, hey, like in general, this is just a general group of people. They really should fit somewhere in this category. And so then you curve your class accordingly. Or sometimes, like professors are notorious for this, hey, most people are actually getting like F's. Like the test is the average is a 40%. So that means it's really difficult. So we're going to do this pretty massive curve. So a 40 turns into like a 75. Which I don't know why you wouldn't make the test just generally a little bit easier. Except it does leave room for people to challenge themselves and say, hey, I aced that test. It was extremely difficult.
Would they then get extra credit?
I don't, usually not. Usually that person that got like a 90, I don't know how the whole curving system works because I don't do it, but they would be increased, probably not up to extra credit, but up to like the 100 scale or something, I don't know. So that doesn't make a lot of sense, except it does allow for people to be really challenged. But if you make the test way too easy and even your chaff is getting like B's, then there's no challenge for those getting A's. It's kind of like, well, it doesn't make sense. So then you would adjust the score accordingly. So the standard normal curve can work. You can force it to work for classes, or it might naturally work for classes. So in other classes, like Algebra 1, Geometry, with more kids and more, everybody's kind of required to take those, you're going to see more of this general look to it. Although most of the kids here, you would say like the demographic is people in general have parents that might be a little more invested, students might be a little higher academically, usually, 2 parents at home that are kind of helping in general. So therefore your middle may not be a C, your middle average may be more like a B. So you go to a different demographic and things will change just because you have a different clientele. Okay, so that's the standard, kind of the general idea of the standard normal curve. If you look at the next data, there on the bottom of 661, they have an experiment. A psychologist asked 100 children to solve a certain puzzle and records their solution times. And you can see that in terms of seconds, 1% of the children solved the puzzle in a time greater than or equal to 25 seconds, but less than 35 seconds. You can see that chart there, and what that chart forms is all that data kind of fits in a standard normal curve. So what it means is, which is interesting, that's kind of a different look in terms of, when you have this and you have this, this probably isn't exactly accurate, but something like that in terms of what they exactly have. But the 25 to 35, there's very few kids that got that, and then whatever it is up to 125 to 135, you have very few kids getting that. So what that means is this kind of fits the standard. If you drew a curve around this, the standard normal curve, you would say, yeah, that makes sense, that it does fit the standard normal curve because most of the data is in the middle, and then you have these very few are on the extremes. So in this case, you're handing a puzzle to kids to solve. You would say the kids that have the high IQ, that's how they do some of these IQ tests, like, hey, very few people actually, so this typically you look at saying like it's a really bad score, but that actually in this case is when you're solving it that fast, would be, you would say, wow, your IQ is really high, or you're a really quick problem solver. So this would be considered like where you're fast and you're doing really well. This would be considered, well, you're a little bit slower processor and not doing well, possibly. So kind of the other way, but the data, the majority fits in there. Now the standard normal curve, when we actually get into the details of it, states, and you can look over at all the data on page 662, it states a couple different things, and if it doesn't quite fit perfectly into this, it can still have the general look, and we can apply the information to a standard normal curve, even if the data isn't perfect. But if we have this look, okay, what the score is like, I know we talked about standard scores, is you wouldn't say, hey, my baby's weight was 6.5 pounds, or 6 pounds 7 ounces, let's say. You would apply it if it fits in a standard normal curve, which like baby weights generally do, head circumferences, baby weights, and their height. And they talk about that, what's their percentile. They're referring to the standard normal curve. And so what it is they would, and remember we talked about your standard score. Typically, nobody refers to your standard score when they talk about your baby's weight, but they refer to your percentile, right? So, oh, your baby's in the 7th percentile. Now that has a standard score. The percentile is actually just referring to what percent of kids they're heavier than, So, but the average, so if they were in the 50th percentile, the 50th percentile is actually just going to be right down the middle. So they're just going to be exactly average. So, hey, your baby's right on par for an average weight of a baby. So they're in the 50th percentile. But their standard score would be 0. Because remember, the standard score, remember the little formula we called it? The z-score was equal to?
X minus the mean.
The mean.
Of the standard deviation.
Or the standard deviation, right? And I think we were, I don't know if I put s dot d dot, or it's the square root of the variance, but the standard deviation. So that gives you a standard score. So if you're average and you're right on the average, it means your score minus the average score is the same thing. So 0 divided by the standard deviation. So what you can have though is you can have a negative z-score, which is your standard score, or you can have a positive, z-score. And your z-scores, when we march out like this, my picture isn't perfect, but it's accurate enough, like 3 and then to negative 3. Okay. So what we know is if it's going to fit a standard normal curve, so I was saying 50% was referring to 50% of your data goes right up to the average, and then 50% of your data is after the average, okay? So with that though, 68% of your data fits within one standard deviation. So in a standard normal curve, 68% fits within one standard deviation. 95% fits within 2 standard deviations. And then 99% fits within 3 standard deviations. So, the majority of your data is going to fit within 3 standard deviations. So if you think about that, and well, we'll talk about that in a second. Okay, so standard normal distribution represents this. That means 68% of your data falls between -1 and 1, right? 95% falls between -2 and 2. Now these represent 1 and -1. Those are your z-scores, but that also is 1 standard deviation away, 2 standard deviations away. You could be 2.179 standard deviations away, right? You can have decimals, so whatever your z-score is. With this, the area underneath the standard normal curve, anybody want to guess what the area is equal to? Think percentages, like I've just been talking.
100%.
Yeah, is equal to 100%. Therefore, though, you would refer to it as the area is equal to 1. But 100% of your data falls under there, which would also just be 1. So the area underneath the curve is 1, but you could think of it as, to make it easy, 100% of your data, because we're referring to percentages right there. So 100% of your data is going to fit underneath the curve. And so this area underneath the curve is just representing how much of your data is in there. So again, if you're in the 99th percentile for mathematics when you take your SAT test, it means you're falling, right? It means you're falling way up here, and that means 99% of all the data coming up to you, you're better than. And so then, you know, if you were at the very, 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 very top, you were the top, you'd be at the 100th percentile. So the area underneath the curve. So therefore, again, like I stated earlier, how much area is up to this? Well, 0.5 or 50%. So decimals, you can think of it as percentages as well. But 50% comes all the way up to here. Therefore, 50% goes all the way over there. It's symmetrical, right? So if you found between 0, if between -1 and 1 is 68%, how much is between 0 and 1? If 68% is between -1 and 1, yeah, this would be 34% there and 34% here, you know. So, you know, that's, but this is always 50%. So some books will describe only looking at 0 going forward, and so then you're like, okay, and you just have to know that 50% is always below that. And so if you're like, hey, I got a z-score of 1, you are not in the 34th percentile, you're actually in the 84th, because you're actually including all of this. But when you look up from 0 to 1, you're going to see 34% or 0.34. But the book, some books will say, hey, we're just, since it's symmetrical, we're just focusing on half of it, knowing that we can add 0.5 or double from 0 to 1, 0 to -1, it's just double. So when you look at page 664, they give you a nice turquoise chart there. This book, I think the Algebra 2 book, just looked at limited scores. Right? They looked at, I think they just looked at half. I'm getting a chart for you. Okay, this chart is an extensive look at the turquoise chart. So the turquoise chart, you can see, just goes to the 10th place. This chart I'm handing you guys is something that actually goes to the thousandth place. You don't have to use the white chart. The book answers are going to be based off of the turquoise chart in your book. This chart goes actually to the thousandth place. I'll hold it up here. Everybody will get a copy of this. So it's just a more detailed chart. Now, if you look at, since you have the page here, if you look at 0.0 on the page with all the positive z-scores, if you're looking at the page with the negative z-scores, and that's fine, you can actually look at either one. If you see negative 0.0, you'll see the decimal, so it's like negative 0.0, 0.00. The decimal is 0.5, right? 0.50000. If you flip it over and you look at 0.000, the decimal is 0.50000. All that's representing is 50% of your data up to 0, right? So when you look at this chart, if you wanted to know like how much data is up to 1 standard deviation, you would look at 1.000, right? And that would give you 84 or 0.84134. Do you see where it says that? At the number 1? 1.000, you see the number 0.84134, right? Mm-hmm. So if you think about 0.84134, what that's saying is it is 84%, and we just talked about that, is that at 1.00, that is 84, they say 0.84134. So remember, 50% of your data coming up to 0 plus 34%, 50 plus 34 is going to be 84%. So the general, like 68%, it's a very close, accurate statement. It's actually 84.134. There's a little bit more tacked in there, but we can just stick with 34%. It goes from there to there.
So what's the top column? Top row for it.
That's if you wanted, like, let's say your z-score on this white sheet, let's say your z-score was 1.07, you would go to the 1 and then go all the way over to 0.07 and march down. And that 1.07, that's your z-score is equal to that. Your percentile is, what do you have, 0.85769? So then what you're stating is that's 85.769%. That's your percentile. So this is a detail to the hundredths place. Your turquoise sheet in your book, if you look at 1.07, they don't have that. Their accuracy is to the 10th place, which is going to be fine. So use the turquoise sheet. I just give this as kind of a reference, but use the turquoise sheet. You can see, like on the turquoise sheet, let's do 1.5 for example on the turquoise sheet. So if you look at in your book, when you look at 1.5, you go to the 1 and you scroll over to 0.5, you're at 0.9332, right? So if your z-score is 1.5, that means you're 1.5 standard deviations above the average, right? And so the z-score is 1.5. Your percentile, the percent of data below you, is 0.9332, right? I'm looking at the turquoise one, 0.9332. Does that sound right? Mm-hmm. So that's 93.32%. So if your z-score is 1.5, it means you're in the 93rd.32 percentile. So if you're doing a test score, you're above 93.32% of the data of all people who fall below you. You're better than, if you will, 93% of the data. In the white sheet here, if you wanted to know a z-score of 1.5, you just go to 1.500, and it gives you 0.93319 on the white sheet, 0.93319, which, if you round that, it's 0.9332, right? So it's the same thing, it's just a little more detailed and accurate. The white I will give you for the test, I believe what I have is, I have a turquoise chart. It's on the test, so you can just use that. If you use the white one, your answers might get slightly off from the book answers because there's, some of the issues of like the rounding issues. Or if you had like let's say you had 1.5 1.45, the book is going to average between 1.4 and 1.5. If you had 1.45, they'll just take your two scores and average those percentiles. So, sometimes there's quartiles. The term quartile is also used. And you can see that in the book. The 75th percentile and the third quartile, same thing. 75th percentile and the third quartile represent the same thing. So, let's do one example, and then I'll just pause there. We can talk about some more examples tomorrow. Excuse me. So if we go to page 667, number 1, it says on a standardized aptitude test, scores are normally distributed with mean being 100 and the standard deviation being 10. So what that states for us is, again, if we were to, so if they're normally distributed, right, and it goes like this, it goes like this, the mean, right in the middle is 100, the standard deviation is 10. So this would be like 110 and 90, right, because they're 10 units away. Remember, your z-score, though, you wouldn't say, hey, if the average was 100, so obviously this was out of more than 100 points, you wouldn't say, hey, I got 100 on the test. For your z-score, you would say, hey, I got a 0. And then if you're like, hey, I got a 110, you wouldn't say, I got a 110, you say, hey, I got a z-score of 1. Or, hey, I got a 90, that means you got a z-score of -1. Next round up would be what? If it's 10 standard, if the standard deviation is 10, you go from 100 to 110, 110 to 120. Now this is a z-score of 2, and there's all these decimals in between. And then if you go to an 80, you're at a z-score of -2, and then 70 would be -3, and then 130 would be 3, so on and so forth. So when you go to look at your charts, you're going to need to do conversions to get your z-scores so you can figure out your areas by looking at the turquoise sheet or the white sheet, whatever you want to do. Now it says, find the percent of scores that are less than 95. So what that states for us is we want to find the percentage of scores that are less than 95. So we look at a score. If you scored 95, you need to figure out what is the area all the way up to 95. And the charts are the accumulation of the areas. So when you read the charts, that number they're giving you, the decimal, is all the area up to that spot. So we need to convert. How do I convert a z, or how do I get a z-score out of a score of 95? Well, I take my 95 minus the average, right? 100, is that right? And then divide by my standard deviation, which was 10. So in this case, I would get out negative, right? -5 over 10, so -0.5 or 1/2. Your z-scores you're going to do in decimal form. And so then you go look in your turquoise sheet and you find -0 and then over to 0.5 because you're in the negatives. You don't want to be 0.5, you want to be -0.5. 0.3085. So the z-score matches to 0.3085, which is what percent? 30.85%. So that means you're better than 30.85%. So you're in the 30th or the 31st percentile if you round it. I'm in the 31st percentile. You bet. So how do you figure out greater? This will be the last one I do, or we can do all 3 of these, 4 of these. Greater than 115. So if I want to know greater than 115, that means up to 115, right?
Mm-hmm.
So it's just a geometry area problem. Total area, right? What's the total area?
1.
1. So total area of 1 minus the shaded area gives you your area. So you just take 115 for a z-score, which is 115 minus 100 over 10. So you get 1.5 for a z-score, and that was, what's 1.5 give you?
0.93319.
0.93319. Oh, that's what we had right there. Nice. And so then you just take 1 minus that, and that will give you, because that's representing 93.32% goes all the way up to here. So how much is left?
6.681%.
6.681%, yep. So 1 minus that gives us this value right there. There's 6% left. Okay, so then it says between 90 and 110. Now, between 90 and 110, you could do a quick rough estimate, right? What's the rough estimate? How much is between -1 standard deviation and 1 standard deviation? Between 90 and 110, there's
68%.
68%, right? Approximately. But to get the better accuracy, you would figure out that you would have with a z-score of -1, which is 90, your decimal for that is, what's your decimal for that?
For
-1, the exact decimal.
-1 is 0.15866.
0.15866, and then your z-score of 110 is 1, and that's going to be
0.84134.
84134. So what that tells you is, right, if you're looking at your curve like this, it tells you that up to here is 0.15866, and then all the way up to here, the whole thing is, all of that area is 0.84134. So if you have this bunch of area is this, and this little area is this, you would take the total minus the tail, if you will, the total area leading up to that minus the tail. So 0.84134 minus 0.15866. So you take the total area, get rid of the tail, and that gives you how much is between 90 and 110.
0.68268.
68268.
Yep.
So that gives you 68.27% is probably, I think that's the book answer, because they say 2.6, which again, if you ended up at 2.7, that's fine, because we're doing the white sheet. I think you and I were using the white sheet. So.
Mm-hmm.
Okay, so let's pause there. It gives you enough to go off of. Let's get started on.